Okay, so welcome to, I think, what might become day one of online learning. We kind of did a trial run yesterday. If for some reason things don't end up working out for you, then there will be a video that gets shared on my YouTube channel. So I just wanted to go over some of the things that we did yesterday. If you can't see, I'm just on our AP rotational motion slides, and what I can do is tell you the slide number that we're on. Maybe that'll be helpful. So let me tell you what slide number we're on. What slide number am I on? Slide 36. Yeah, we're on slide 36. Okay, so yesterday we did this slide and we did some calculations. So you're going to see the work that's already shown. But the main concept that we talked about last class was that translational kinetic energy can be added to rotational kinetic energy. So for this is for situations where you have something that has a linear velocity and something that has a rotational velocity as well. Hold on. People are telling me that it's paused. Can y'all hear me though? Oh, okay. Then I haven't changed anything, so it's fine if it's paused. Okay. Um, so we did this problem, and it's an object that's, I guess, falling and spinning. So we had to keep in mind that if we wanted to just look at the linear velocity, we would have to use translational kinetic energy for that. And then we take the rotational kinetic energy that has the formula of 1/2 moment of inertia angular velocity squared and find the kinetic energy rotational. And then you can add those together. And the whole reason we had to go over this topic is because we had number 9 on the rotational motion problems. So let's let it see if it'll unpause. What does it mean, swap to your game to resume? Because that's what it's telling me. Yeah, it's popped up in another window. Okay, hold on. Sorry, y'all. I guess I'm a boomer because I don't know this new technology stuff. Only have one window open. Okay. Let's try that. Only one window open. Are you sure I'm sharing my screen? It doesn't look like it. Uh, Oh, change screen. I see it. Oh, okay. I got it. Thanks. That was you, Sarthi, huh? Yeah, hold on. Yeah, Justin, I can't hear you because I muted you. Okay, hold on. I'm still playing with it. Yeah, it's still telling me stream pause. Swap your game to resume. Why won't it let me show the screen? Come on, work. I think what a big problem is I'm trying to record and do this at the same time, and I don't know if that's going to work. I'm trying. Oh, Mr. Wadzicki's here. Maybe he can figure it out. Sakura, warm up time has changed to figuring out how Discord works time. Y'all play too much.
What are you trying to do?
Oh, I think it just kicked me out. Yeah, I was live and then it kicked me out. See, it's telling me that swap your game to resume. And I'm trying to get it to show the screen.
Why don't you put that window up on the second monitor?
Okay.
Just pause the screen if you see your features.
Okay, so now it says it's running. But I just can't.
Can I see it?
Can you? Yeah, y'all can see it, right? Okay, I'm gonna put the stream quality down, maybe.
They might not be able to read it. Change the frame rate. Change the frame rate lower. There you go. Because it's snapped. They don't care about frame rate.
Okay. What about now? Can y'all see it? No. Okay.
What if you cancel it? Rate?
Okay, hold on.
Okay. Yeah, you click that. You said no what this is. What is screen?
Oh.
Two.
Okay.
What's your stream rate? Okay, try that. Stream 4. So what? 2, 8. Okay, so click on this window then. There you go.
Okay.
So when you're
Are
in
we
Discord,
good?
it pauses. But once you're in there, it should be.
Okay, y'all see number 9? Okay, and you can hear me. Me? I'm cutting out a lot. A lot.
Try for me.
Okay, I changed the quality a little bit. How about now? It's legible. Okay. Well, I mean, you guys have a copy of the slideshow anyway. I sound good and I can see the screen. Okay. Thanks, Vaughn. Y'all, you have no idea how much I appreciate you being patient with me. I mean, you guys always are patient with me, but I'm just trying to do the best job that I can with what resources I have and y'all have. And I'm trying to be fair by videotaping and doing Discord and doing that and holding office hours. So, I hope you guys just realize that I'm just doing the best that I can. Okay, so this is what we did yesterday. I talked about how we did this problem. Then we used that idea to solve number 9. And the next slide that I put here is the derivation that we did last class. And we did that derivation because that's what you had to do for number 9. You had to use energy in order to solve for a disk rolling down a incline, because we did problems like that before where we said um, a object is moving down an incline but not rolling, and we would say that all the gravitational potential energy would then be converted straight into translational kinetic energy. And that's not what we can do anymore, because we can go to next level. We can say, oh, well, the disk at the top now has translational kinetic energy, it can have rotational kinetic energy, and it can have gravitational potential energy. And all that energy that could be happening at the top is going to be equal to the bottom. So in the derivation, you see that kinetic energy translational. Who's yelling? Victoria, is that you? Quit yelling. Well, we're on the AP rotational kinematic slides. So yeah, we're looking at slide 38 right now. Yeah. So I'll try, if your internet's not working very well, which I just had some problems, I'll let you know what slide we're on. You just have to type in the go live stream, just say I can't see anything. Okay, can you see it? Okay. So there's no translational kinetic energy at the top. Um, but there will be kinetic, translational, and rotational energy at the top. So we did this really long derivation yesterday, and we found out that if we want to find the translational velocity at the bottom, well, the formula is just square root 3/4 gravity times the height of the ramp. So for number 9, if you haven't solved it yet, basically the formula is velocity equals square root 3/4 g h, and you would get the correct answer, which was supposed to be like 3 or something. I can't remember. Hold on, let me look at my notes. I didn't even write down the correct answer. I don't know, but 3. Yeah, it's supposed to be around 3 meters per second. Okay, so you can use this derivation that's on slide 38 to solve for number 9 on your rotational problem set. Can we just do a quick update for me on how the rotational problem set is going? Like, how many more problems do you have to do? Because I asked for those problems to be submitted on Google Classroom, and I'm not really having a lot of people submit those. And this is what the purpose of office hours is going to be. I just spent like half an hour talking to one of my students, and we solved 3 problems together. So We can video chat. You can just call me on here, and we can do problems together. Okay, well, after this, if you want to solve those, it seems like there's people that say they have two more or three more to do. Just let me know, and I can stay live, and we can do those problems together and solve for them. Okay. So I'm still kind of talking about what we did yesterday, just to have the video updated for everybody on what I've been covering. So we went through these questions, and we talked about basically what happened in our torque stations before we left for spring break. So I'm on slide number 39 if you can't see my screen for some reason. And we just talked about which wrench would be most effective for tightening a bolt. And that would be this last one here, because in one of the stations, actually two of the stations, you should have realized that as the lever arm or the radius of the wrench increased, then it became easier to rotate the bolt. And that corresponds to the formula for torque being force times radius. Your larger radius is going to give you a bigger torque, which will move your item that you're trying to rotate more. So then we went over size of the force, and we found that, again, number 3 has will apply the most torque, because as you add more force, then you're going to give it a greater torque, which would tighten the bolt or loosen the bolt better than the other two. Then the last one we went over was looking at the angle, and just remembering that the angle is most effective at 90 degrees. Okay, so now we're kind of into the new stuff. Let me just do a check and, make sure people can hear and see the screen. So this might be the point where you want to have like paper, notebook, something, because we're not really into new stuff. What I'm doing, guys, is I'm just clarifying. So right now I'm on slide 42. If you can't see. On the rotational motion. Okay, so we're on slide 42, and it says torques exerted around a common axis can be added together. And we have this situation of some forces that are spinning an object. So if we want to calculate the total torque exerted on the disc, then we have to understand the formula for torque. So can somebody type in the formula for torque? Thank you. Torque equals force times radius times the sine of the angle that it's applied to. So let's take a look here. The sum of the torques, torque 1 plus torque 2 plus torque 3 plus torque 4, we would add all of those together, and we'd have to look at each torque in terms of the equation that was listed. Force times radius times sine of the angle. Now, one of the things that we need to write down here on slide 42 is that we have a major assumption. Our major assumption that is if the torque is going clockwise, then it's a positive torque, okay? And if the torque is going the opposite way or counterclockwise, then that's going to be considered a negative torque. And the way we can see that is within the angle. So let me give y'all a second to kind of make those notes that clockwise torques are called, or if it's a positive torque, then the object is going to move clockwise. If it's counterclockwise, then the torque is considered to be negative. And we'll see an example shortly. What do you mean stay like that? Yeah, so that's a good comparison is when we talked about linear forces, that forces to the right are positive and forces to the left are negative. So now since we're talking about objects that are spinning, we're going to say that if an object's moving clockwise, then there's a positive torque. And if an object is spinning counterclockwise, then there's a negative torque that's applied. Yeah, good question. Thanks, Sarthi. Okay, so I'm just gonna let the slide kind of calculate everything for us. So when we do this calculation, the angle takes care of the negative and positive parts. But what I want to point out to you is if we look at the torque 1, the force of 4 newtons, radius of 7, and sine of 90, that if we look at the direction that it's going, then that's moving clockwise, right? That force is in a clockwise direction. So then we know that clockwise should be positive. So that's why it's listed as a positive. Over here, for torque 2, it's at sine of 140. So if I drew that, sine of 140 is pointing in that direction. So if I look at the y components, because there is a y component, the y component of that force would be moving counterclockwise. So that's why they put a negative sign in front of torque number 2. Then going over here to torque 3, okay, the one that is 9 newtons times 4 sine of 90. If we look at where that vector is, then that's moving counterclockwise as well. And then looking here at the last torque, where it's located is moving clockwise. So then that's why we assigned it a positive number. So if somebody has their Desmos calculator or just a calculator, I would like to know what the sum of these torques are. Is that Gabe again with the right answer? With the units. Good job, Gabe. That's correct. So now that we have that negative, what's the significance about the negative? Does that mean like a negative torque? What's the significance of that negative? Moving clockwise. Ooh, I don't know, Jayla Bean. Yes, it's moving counterclockwise. So it's kind of cool. I mean, we talked about for linear velocities and accelerations that the negative is just a direction for us. So that's how it's going to act in torque as well. That it's going to be directional. Positive torques would be a clockwise torque, and a negative torque will be a counterclockwise torque. Okay, so that's one of the concepts that I'm discussing today. And we're going to go ahead and also go back to Newton's second law of rotational motion. Okay, so we took notes on Newton's second law for rotational motion last class. So just find it in your notebook. Yes, Victoria, your answer would be different if your calculator is in radians. Let me just check. Yeah, it should be in degree mode. Okay, so we discussed that the sum of the torques can equal your moment of inertia times your angular acceleration. And just a clarifier here, I is also known as rotational inertia. So you can say I is rotational inertia and or moment of inertia. Those terms are the same. Rotational inertia is, what did I say? Moment of inertia. So I need to check something that I just realized. I have somebody asked me in another stream if there was if this is going to be recorded. So I'm just making sure that the software that I have is recording in the right place, which I think it is. Well, I mean, we'll find out, of course, when I'm all done. Okay, so we went all over this, and we did a kind of like a derivation where we just took Newton's second law for translational motion, and we just changed everything to make it into rotational motion. So there's the same rules here that we had in Newton's second law for translational motion, that if there is no force applied, then there's going to be no acceleration. So it's the same concept here. If there's no external torque, then there's going to be no rotational acceleration. So this statement here says an external torque will exerted on an object will cause the object to have rotational acceleration in the same direction as the external torque. Okay, and we have to remember something. One of the concepts that we got confused on, one of the first ones we got confused on, is we would say these things like, oh, if there's no acceleration, then there's no velocity, which we learned that that's really not correct. That if there is no acceleration, that doesn't mean that there's going to be no velocity. It just means that it could be moving at constant velocity. So this scenario goes over too, that if there's no external torque, then you can still have constant angular velocity. Okay, which remember the angular velocity is the omega symbol, and the alpha symbol is for angular acceleration. Okay, I'm just gonna pause for a minute and make sure nobody has any questions or comments about that idea. It's like I said, the same idea that we talked about in Newton's. Oh, Chick-fil-A? Y'all, are you gonna come out to Tomball and drop it off? The direction doesn't change it then. Yeah, because good point, Victoria, because if direction changes, that's a form of acceleration. Yeah, Gabriel. So if the sum of the torques equals 0, there'd be no angular acceleration. Yeah. Because then that would make the left-hand side of the term be 0. So then everything becomes 0. Well, we were looking at 4 torques on one system, Gabriel. So that's kind of what we have to keep in mind here is we're looking at a system, not just a point. Yeah, so that whole, let me go back to the slide. This whole thing is a system that had 4 torques on it. So we're looking at the angular acceleration of the system. Good question, though, because that brings back that whole topic of the system. Okay, so here's a problem that we can solve to let us know what these questions are going to look like on Newton's second law for rotational motion. So what this problem wants us to do is calculate the rotational acceleration, or alpha of this thick disk. So I'm going to give you guys, I think, a few minutes to see, or a minute or two to see where you want to set up this problem. But I'll start you off. Is remember Newton's second law of rotational motion is the sum of the torques equals moment of inertia times angular acceleration. So go ahead. We're on slide 45 if y'all aren't with me. And we're solving that problem. Oh, I muted myself for a second. No, I just gave everybody some time to solve slide 45. Victoria, that's what I got, but I have no idea of what your units are, so I'm going to say that's wrong. And Gabriel, you got to get out of this habit. You got to start doing the full derivations and stop doing it in parts. Yeah, 1.25 is right, but I need the units. Gabriel, we're not solving for tension, we're solving for angular acceleration or rotational acceleration. You're not slow. Good job, Victoria. That's correct. Okay, so I might mess things up, but the screen that I have this on, I can't write on it. So let me see if I can change it. I think that will have you guys see my, hold hold on, give me a second. Okay, hold on, I'm playing around. And I think Discord's about to get really mad at me. Do y'all see anything right now? Yep, Discord's mad at me. I don't know if y'all can hear me or not, but everything just froze. Who put Okay, Discord's like really mad at me. Ugh.